Since 1973, he was a co-founder of a factory for thermal solar absorbers. Okay.
Thank you, Mr. Chairman. Kalispera. Good afternoon. It's a big pleasure for me to present you some words about indoor environment quality and energy. They are fighting or going together. I'll show you they are going together, especially in Mediterranean climates. This is the outline of my speech. After an introduction, I speak a little bit about design intention, but rather short because some other speakers already present good ways to make good design, and will insist on especially thermal comfort. It's one of the many comfort, but I will speak specially on thermal comfort, and hence about heating and cooling. You certainly remember Vitruve, who has 4 principles to erect a good building, and within these principles, commoditas, in Latin, is one of them. The building should be comfortable and healthy. That's Vitruve. It's an old history. Now, with a new requirement of sustainable development, we add the 3 pillars of sustainable development, that is environment, friendliness, social aspect. This includes comfort and health and economy. So these stakes should never be forgotten. HOPE was a European project aiming to see if low-energy buildings are more or less comfortable and healthy than ordinary buildings. The answer, final answer, was clearly yes, low-energy building are more comfortable and healthier than ordinary building, but I just want to show here the definition we took at the early beginning. What is a healthy and energy efficient building? It's not only low energy, but also has ensure a high level of comfort and, of course, doesn't cause or aggravate illness. We need energy to improve comfort. In fact, we need energy to do anything. Energy is what we need to do something by definition. So we cannot do anything without energy. And if we miss energy, the comfort may decrease, of course. But the good question is, are we more comfortable when we use twice as much energy? Do the Americans live much better than we do in Europe? They use twice as much energy per person, per capita, than we do. And I think we can clearly answer no to that question. We don't. And it was Flu's saying next room this morning, we are not more comfortable when we need more energy to cool down the building at 80 degrees, 18 degrees, sorry. So there are ways to improve both energy use and indoor environment quality. Buildings are designed with several different objectives. The first one, indoor environment, in my opinion, is the main objective. I'm sure you agree with me, is the main objective to design a building and to erect a building. The other are just secondary objective. Prestige, image is not essential, but if somebody has a big pleasure to make a beautiful building, which is at the same time comfortable and healthy, why not? Low cost is an issue for sustainable development, is the economy pillar, but it's not an aim by itself. I was told about hundreds of residential buildings that were erected for low-income people, and therefore they were low-cost building, and with no insulation and with penny heating system. It was in UK. And they got a lot of mold growth problem just because it was low cost, the only objective. Energy saving is not an issue by itself. It's a side issue, because if you erect a building with the only objective to save energy, you better not erect the building, of course. That's obvious. And real estate is not an objective, it's a tool. Capital is needed to erect a building, but the guy who gives you the capital needs some reward, but it's not an objective by itself. It should not be. It is in many cases, but it should not be an objective by itself. An issue I like much is the indoor environment quality, the first stake, in my opinion, can be obtained by passive or active ways. Passive ways are architectural and constructive ways to reach the objective of good indoor environment quality. And active ways are technological means controlled generally by an engineer with the same objective. These two may be opposite, but in fact, I'll show you they are complementary. As example, you know, it's obvious, passive ways are thermal insulation, thermal inertia that stabilizes the temperature, natural ventilation, natural light, daylight. Also, don't forget sound insulation, sound absorption. All these systems are passive. They don't need expensive energy. The energy they need is just free energy that comes from, that doesn't pass through a meter. You don't have to pay for it. Active ways, you also very well, you know this list: heating system, mechanical cooling, ventilation, artificial lighting, background music that is sometimes used in shops to cover the background noise, and so on. Both ways have advantages and disadvantages. I put the advantages in green. Passive ways are cheap. They are part of the building, and building with well-designed from the passive point of view are not much expensive than building built without thinking about that. So passive ways are generally very cheap. They need a little bit more thinking, but the architect and engineer are not that expensive, you know. They need energy, of course. When I say they need no energy, they need no expensive energy. They don't need energy that goes through a meter. They never break down. Gravity doesn't break down. The sun exists still 4 billion of years and will still exist for 4 billion of years. And it will not break down for a long time. But the disadvantage, the availability of the passive ways is not that good. We don't have daylight during the night, and, natural ventilation, sometimes the wind is not blowing or the temperature difference is not good enough. So they are more difficult also to control. The active ways are expensive. They are added to the building, and mechanical ventilation system is very expensive compared with just a controlled opening. They use expensive energy. It can be renewable or not, but it's expensive. It's added. They may break down, and when you count on air conditioning or cooling, mechanical cooling to be able to live in a building and it breaks down, you have problem. Recently, this year, there is a big new tower in Zurich, and it was an electric breakdown, and they had to evacuate it. People couldn't stand in that building because of an electrical breakdown. There should be something wrong in that building, of course. But that's a big advantage. The active ways are available as long as we have energy and we can pay for it. They are easily available and easily controllable when by a button you just switch on and off. You turn on the thermostat, and it's rather easy to control. So this table clearly shows that for each green line there is a red one and vice versa. So these two ways are clearly complementary, and they should be used both. But since passive ways are cheap and use no expensive energy, I propose to use a design strategy, of course, that give priority to passive ways. And as I has heard already today, I'm not the only guy who proposed this. It's well known now. And when and where needed, and I will insist on that today, only when and where needed to complement with active ways, not to start with active ways and add passive one. The contrary. Generally, this strategy leads to cheaper active system, smaller, cheaper, and most interesting for architects, it gives much more freedom. Past century in Switzerland, we had single pane windows, and we had to put radiators below the windows, taking the ducts to these radiators and taking space under the windows to avoid condensation and draft. With new glazing, it's no more necessary. You can put the heating system anywhere you want, and you have a perfect comfort. So it gives much more freedom. And as we have seen from the HOPE survey and other European projects with this objective, the indoor environment quality is better in passive building. When I the narrow German concept is just building that are well designed. So I will not take a long time for design recommendation because there was already one speech today on this very issue. Important is stakeholders should have good intention. We have seen also in Hope Building that the best one, those who were at the same time energy efficient, healthy and comfortable, were designed for that purpose, and it was the intention of the owner of the building first, not only the architect. It was the owner started with that intention, and this is maybe the first condition to have a good building is the owner should have that intention. Also decision, this was not told today, but it's well known. The earliest decisions are the strongest. And at the very early of the project, we have a large freedom. You can take every possibilities, and it's the good time to choose between different ways. If you start, I was asked by architect, please, Claudal, change my drawings so that I can get the Minergie label. And the drawing were ready for publication. So, and it was, in several cases, too late because it was no more possible to make this drawing, to reduce the energy use of this drawing in such a way that it can get the label. So the choices should be made very early. And they are the most efficient. And, I repeat, prefer passive to active ways. Finally, the design also should be made for the user. The building should be user-friendly. I come back to commoditas of Vitruve. The building, I hope there are not too many architects in the room. The building should not be designed for the architect's proudness. It should be designed for the user. It should also, and that Fluensu in the other room this morning has shown that very clearly, the building should be adapted to the environment. I start with one environment, among others, adaptation to noise. And one way is to take urbanistic measures. I mean, putting buildings that need quietness in quiet areas and buildings that make noise in noisy area, separate them. That's one way. The other is to adapt acoustic insulation. Also adaptation to pollution. Again, so we can take urbanistic measures, including transportation, public transportation measures. But also, at the building, we can locate air inlets on the roof when the air is a little bit cleaner than close, where I've seen that in a building in Lausanne. The air inlet was near the diesel bus stop. May not be a very good idea. And finally, last but not least, they should be adapted to climate. And this is the introduction to the thermal side of my talk. And I like very much this sentence given to me or to an audience in a conference by a professor in Grenoble. The building should be with all systems off. The building should be free running, when free running, at least as comfortable as outdoors. Think about that. There are buildings that are much less comfortable than outdoors if you switch off all systems. And can illustrate this way. You can see from through the year the outdoor temperature that can vary, go up and down from one area to the other, or can be steeper or more flat. But anyway, it changed during the year, and the comfort range also changed throughout the year. In summertime, we have less clouds, and we need a higher temperature than in wintertime. And that's well known for the adaptive comfort model I will speak in a minute. If I take a poor building, it will always be warmer than outdoors because of internal gains. And in summertime, it could be very uncomfortable without cooling, and in winter, also very uncomfortable without heating. It's possible, I will show you, in Mediterranean area to have buildings that are nearly all the time within the comfort zone. And it's what I speak a good building. And of course, the cooling season and the heating season of a poor building are much longer than for a well-designed building. Energy and indoor environment quality was, from some people I heard sometime, well, new insulated buildings are less comfortable because we have a mold growth problem or poor indoor quality and so on. This was true for some buildings, unfortunately. For example, for the 100 dwellings I spoke 10 minutes ago. But this result for past errors, just after the oil crisis, the only purpose was save energy, save energy. And if only that in mind, you can make, if only one objective in mind, you can make a lot of errors. We are obliged, in buildings at least, and for many other activities, we are obliged to have a large view. And it's the task of the designer to take every stakes into account. And that's the difficult task of the architect. That's why I admire them. I'm a physicist. And you can see in the paper, which should be on the site, or will be on the site, I put a table of many ways to improve at the same time indoor environment quality and energy efficiency in buildings. So I will not spend time here now for this, but go into showing something about thermal comfort. To improve thermal comfort, there are several ways. In cold season, we have to increase thermal insulation. Increasing thermal mass may help to take advantage of solar radiation through the windows. The solar protection will help you to control the solar heat where needed. Controlled ventilation, I guarantee a good indoor air quality without having too high airflow rate. And with all these systems, you can take advantage of passive solar heating. Let the sun goes into the home when needed to heat it. And finally, if this doesn't suffice, you can use heating. In warm season, increased thermal insulation protects you from heat. High thermal mass stabilize the temperature between day and night. Efficient solar protection are basic to protect you for solar heat. The draughts, but controlled draughts, feel you more comfortable. And with all these systems, you can take advantage of passive cooling. I mean, ventilate a lot during the night, during the cold part of the day, in order to cool down the building, at a comfortable level, and so that the building has a peak temperature the day afterwards, much slower, much lower than without this system. And finally, you can use mechanical cooling. You see there that 3 lines are identical in warm and in winter and summer, and we are lucky we don't have to change the building between winter, and we don't have to have a summer building and a winter building. The passive design helps you to stay in your house the whole year long. That's a good luck. An important point about thermal comfort are the requirement for thermal comfort. There was a big audit within ASHRAE. They audit several ASHRAE chapters in many countries all around the world, audited 160 buildings, looked at which is the comfortable temperature from the occupant point of view in this building. At the same time, they measured the outdoor temperature, the average outdoor temperature. And in air-conditioned building, we see that the points, 1 point represent 1 building. It's a big dispersion, but they are more or less aligned along a blue line, which is adjusted. The blue line is the mean square difference line aligned on these points. And the yellow line is the prediction of the Fanger model, the ISO 7730 standard for conditioned building. And they fit very well. So Fanger model or ISO 7730 model, which is based on Fanger work, predicts very well the optimal comfort in air-conditioned building. But when we go in naturally ventilated building, the figure is completely different, and the best fit line is much steeper, and the yellow line no more predicts the comfort in naturally ventilated building. This diagram taken from a paper from Drager and De Dier and Brager clearly shows that ISO 7730 doesn't apply to naturally ventilated building, to free running building. And therefore, we have 2 models, 2 comfort models. One, ISO 7730 for conditioned space that are either heated or cooled, and the Dier, Brager, Nickel, and many other people, I was not among them, that resulted in an annex in European standard, 15215, for free running spaces. These lines are just optimal comfort line. If both lines have a slope, it's because in summer we have less clothes than in winter. These are ideal comfort lines, but of course we have some tolerance margin around these, plus minus 10%, for example, dissatisfied around this tolerance margin. And this is the comfort range for office building or living room in residential buildings for sedentary activity. And this one is for free running building, naturally ventilated building. The area up there in summer is comfortable if the building is naturally ventilated. It's no more comfortable as soon as you install HVAC or install cooling. I know I'm not in favor of ASHRAE, so of HVAC engineers, because I recommend to not install cooling whenever possible. Of course, when it's too cold, the conditions are those of conditioned building, because when it's too cold, we have to heat the building. But in summertime, there is a big energy-saving potential with a good comfort. People are satisfied in the green area, and we need much less energy. I will show you that with a few examples on the basis of a single office building This single office room with windows on south facade. And this room is surrounded by identical rooms, so that makes the model simpler, simulation simple for me, and it's just for an example. It's 5 meter width, 4 meter deep, depth 3 meter high. I used Dial Plus for simulation. This room has a massive construction, concrete slabs, masonry walls, including the facade. It's important. And I introduced there the usual occupancy, just for an example. What I changed in the simulation is first the insulation level. First is a typical building here, no insulation, single pane windows. So the walls is made of masonry and that's it. Second, I added outdoors 5 centimeter thick insulation and double pane, ordinary double pane glazing without any infrared coating, for example. And third example is 10 centimeter external thermal insulation with good glazing with selective coating. For most simulation, I used Venetian blind, not the way people used it as Fluensu showed this morning. I really used, each time the solar radiation is too high, I closed them, or the computer program closed them, and taking up when heat is necessary. And the same for passive cooling. Passive cooling was used when necessary. I mean, big ventilation, large ventilation rate during the night by opening the windows simply. I took the climate in Athens. In yellow you see, or green, you see the comfort range for a naturally ventilated building, the comfort zone. And it's the operative temperature, that's the felt temperature by people in the street, versus the running mean external temperature. Why the running mean? In the adaptive comfort model, the people who developed this model have seen that we need some time before, a couple of days before feeling too hot. The first hot day, well, we're happy. Finally, we have a nice weather and it's warmer. But after several hot days, we begin to complain. So they take the running mean to smooth a little bit the peak temperatures. And we see that Athens is sometimes too hot and most of the time in the street too cold. And if I do the same throughout the year, I see a very long heating season outside. So a long time when the outside the temperature is below the lower comfort limit, which is the blue line. The upper comfort limit is the red line. First example, in order to avoid AC, air conditioning, or cooling, could be radiant cooling, we have to use the solar protection. That's mandatory. I've seen very few buildings, especially office building in Athens, with solar protection. I mean, efficient solar protection that are outside. We see that there are many hot hours above the comfort zone, and of course there are still cold hours below the comfort zone. In this simulation, I kept the solar protection off, so up, but use night cooling. In this simulation, I used solar protection, but no night cooling. It's much better. If you cannot open the window, at least pull the solar protection down when needed. And for architect, at least install solar protection or include solar protection in your design. And with solar protection, night cooling, with a middle, slightly insulated building, I don't need AC anymore. There are no more hours above the upper limit for normal internal load. Of course, if there are many people in that building or high activity, air conditioning may be needed. We still need some heating. But to reduce heating, I just take a building with solar protection, with night cooling for the summer, and look what happens in winter with thermal insulation. Without thermal insulation, there are many cold hours if there is no cooling. With a little bit insulation, the number of cold hours are reduced, and the minimum temperature is strongly reduced. It's 16 degrees, nearly comfortable. And with 10 centimeter insulation, good glazing, most of the hours are within the comfort zone. We need only a little bit heating during the winter. This with Athens climate. The same thing for the season. Without insulation, the heating season goes from November to April, May. A little insulation, it's December and until March. And with good thermal insulation, a few hours in December, January, and February. And that's the main effect of thermal insulation. We also have seen that at the LISO building. The heating season in the LISO building, which is good passive solar building, is strongly reduced when compared to ordinary Swiss buildings. From the cold and hot hours are hours above the comfort limit. Cold hours are hours below the comfort limits. You can see for outdoors, there are many cold hours. If I take advantage of solar insulation, solar protection and passive cooling, there are still no more or nearly no hot hours, but the cold hours, and these cold hours are strongly reduced with insulation. If I have a slightly insulation facade but no solar protection, the hot hours are much larger, there are much more hot hours inside than outdoors with normal ventilation and also increased ventilation when it's too warm inside. And for energy point of view, the effect of insulation with solar protection and night cooling, we can see the dramatic reduction of energy use when increasing the thermal insulation. This is for climate of Athens. It's very likely more or less the same situation for all around the Mediterranean. Of course, in North Africa, it could be a little bit changed, but there is an advantage. I've seen, for example, for South Algeria, there is still an advantage to have some thermal insulation. I'm not a salesman of thermal insulation, I would say. Finally, as a conclusion, my first proposal for Mediterranean climate is to adapt, to take advantage of the adaptative comfort model developed and normalized in EN 15250 for naturally ventilation building. In Switzerland, we are now adopting a new version of a comfort standard, saying that all buildings should be designed to be comfortable all over the year without cooling. If you can't because of internal load, not because of solar load, but of internal load, then you can use artificial cooling. Of course, Switzerland is colder than here, so I will not recommend that standard, but at least take advantage of this possibility to not install cooling. And also, of course, use passive design. I will not go through that list because you have seen it several times today, and very likely you all know the base of passive design. A few examples not to do. This is a building in Paris, the Grande Bibliothèque, which is not comfortable for books. So it has to be climatized for the books. I don't speak about the readers, but it's not comfortable for books. This one, I took this picture in New Delhi, Gurun. It's a good example of air-conditioned solar collector. There are people in that building. You see the internal solar protection. They are not efficient at all, of course. And this big glazing, transforming this building into a solar collector. I found this picture very beautiful for a good, an example of what not to do. And I've seen this one in Barcelona. It's a station in Barcelona, again, a solar collector. But I must say, I have no photographs from Athens, but I've seen many such buildings from the airport to here yesterday. And I would recommend to architects not to design this kind of buildings anymore. Last word is about climate change. Everybody knows that climate change will decrease heating energy use.
5 minutes.
No problem, thank you. Climate change will decrease heating energy use. For Portugal, I've seen that it's about 30% decrease heating energy use. Normally, Portugal buildings, if they're well insulated, they don't need energy for heating anyway. But it will strongly increase cooling demand in existing buildings. I've seen in Portugal or Spain can double or quadruple the energy demand for existing buildings. And in Mediterranean countries, there are many, of course, existing buildings that are not protected against external climate, not insulated, no solar protection. Many of them are conditioned. So my proposals are strongly enforced by this climate change. And finally, well, I hope you have understand that, in my opinion at least, appropriate design means appropriate design using passive means allows to, at the same time, have a cook and to eat it, I mean, to improve comfort and decrease energy demand. Unfortunately, for this regulation, for the experience I have, regulation is required. The market will not do that by himself. I'm convinced that the market will not and cannot do that by himself. And we have seen that in Switzerland, in many other countries. Improvement in building energy performance comes only when the regulation is there and asked to do it. I'm sorry for that, but human beings are not smart enough now to avoid the regulation. I thank you for your attention.